So in this video, we're going to continue our discussion of relativity in space and time. And in this particular video, we're going to look at length contraction, which is looking at how different frames of references view distances or even lengths of objects when they're moving relative to each other. So that's really the first blank what we have here. It would stand that if time is relative to your frame of reference, space would be as well. So we're not going to go through as lengthy a derivation. We're going to kind of pick up where we left off with the idea of time dilation or time measured in different frames of references. So to illustrate this, we're going to look at a supposed hypothetical space traveler going to a nearby star where they're traveling at a considerable speed, near the speed of light, and they're going to Alpha Centauri. So we have two frames that we're looking at here, and I'm going to label this one S because we are from the frame of reference of the Earth, so that's going to be assumed our stationary frame of reference. And then what would someone in the spaceship see of the exact same journey? And so, like before, we got to distinguish between two sets of times as well as two sets of distances as measured by each frame. And it can get confusing, and we're going to define eventually something called proper distance. That will be defined more stringently later, but we'll just jump into it here and then try to work things out. Okay, so let's look at our first situation. So we are observing here on Earth. We have our spaceship traveling with V, and we are measuring on Earth. I'm going to put a prime here, delta T prime. Okay, not the proper time, delta T naught. So we got to remind ourselves, why is this? Why is the, and I'm going to go down here. Okay, so relative to the Earth, how would we calculate the time it takes for the space traveler to get to the Alpha Centauri? And the reason it's that is our clock, remember, our clock is moving. In other words, the clock on the ship is what's moving, and we're trying to measure how much time is ticking off on their clock as measured by us here on Earth. And that's a fairly simple expression. It is equal to the distance traveled, and I'm going to put the naught there. That's the proper distance. We'll define that in a little bit, and divided by simply how fast the spaceship is traveling. So we see up here it's traveling with some speed v. All right, so that's pretty straightforward. I'll define it later in another note sheet, but proper distance is the distance as measured in the rest frame. Okay, so since we're in the rest frame, the destination Alpha Centauri is just sitting there, okay, and we're not moving, so we're watching the spaceship move relative to that. Okay, so now let's switch to the different frame, the spaceship's frame, which is figure B. And you can kind of already see what they're going to see there, but recall, they don't see themselves moving. In fact, Alpha Centauri is coming at them at a velocity v, and the Earth is receding with a velocity v. All right, one toward and one away. Okay, so since their clock is not moving, right? If they look at their clock, they're not moving. It's the Earth's clock moving. They would measure a certain time, and that would be the proper time, delta T naught. And by relativity, the derivation we did earlier, how they measured their time relative to how the Earth measures their time is simply equal to delta T prime divided by the Lorentz factor, gamma, where that is an indirect measure of how fast they're going relative to the speed of light. So it follows then, if we do some simple substitution, right, if delta T prime back up here is L naught over V, we can transform that into L naught over V, and then we have the gamma factor. So again, the time measured on Earth is simply a distance divided by speed. The time measured on the spaceship is also a distance divided by speed, but with the gamma factor thrown in there to account for the differences in how they measure time. So if we rearrange this, we see that delta T naught V, right, I'm just cross multiplying, or at least one part is the proper length divided by the gamma factor, And if we do then a simple substitution, this value, v times t naught, is simply the length traveled here, right? Or the length, excuse me, I should say the distance measured by the spaceship between the Earth and Alpha Centauri, because it's coming at it at a certain v and a certain t naught. So long story short, we have the length as measured in the spaceship that the star travels towards it, the distance it travels towards it, is equal to L naught over gamma. So there is our, and since gamma is always bigger than 1, we see that the length measured in the spaceship is smaller than the length measured on the Earth. So we call it length contraction. Okay, so that's what this is. In other words, the distance L between Earth and Alpha Centauri as measured in the spaceship's frame is contracted. So we have from the Earth, time is dilated on a spaceship. From the spaceship's frame of reference, the distance is contracted. Okay, so now let's go to a simple example of this. Actually, don't think I want that. Okay, so let's put this, like I said, the example. So let's say Alpha Centauri is 4 times 10 to the 16th meters from the Earth. Rocket travels at 99% the speed of light, and we could ask how long, a bunch of questions from each frame. And so this is really important that we are clear on our proper distances and proper times so we can use the correct equations, because it's very, very easy to mix up, and it's something that I still have to kind of look at very carefully. Okay, so let's look at the first thing, the 4 times 10 to the 16th. And that's an L. The question is it the proper length, L naught, or is it the length as measured by the space traveler of the actual distance between the two objects? Okay, so pause this and think about it for a second. Okay, so since we're on the Earth, this distance is measured from the Earth, and the Earth is not moving, right, as discussed earlier, this is going to be the proper length. Okay, this was not measured from the spaceship's frame of reference, so that's important. And then we can ask, how long does the journey take as measured by an experimenter on Earth? Okay, and so to choose the proper equation, we got to determine, are we looking at the proper time or the time measured where the clock is moving, and it's where the clock is moving, so this is ultimately the t prime that we want. Okay, so that helps us find the proper equation. If we go to the other side, I'm not going to flip over, we see that t prime is simply equal to L naught v divided by v. Okay, so this is the 4 times 10 to the 16th meters, and v we're going to put in 0.99 and times 3 times 10 to the 8th, which is for all intents and purposes 3 times 10 to the 8th, but we'll just write that there, and we get 1.3 times 10 to the 8th seconds, which is, if you translate that to light years, you don't have to, but that's the standard distance at Alpha Centauri. Okay, so from the Earth, they're going to take 1.3 times 10 to the 8th seconds to get to the star there. But what is measured by the astronaut on the rocket? So before we do that, we know there's going to be that time dilation, so we want to use the gamma factor, so let's do that. So I'll do it right here. Gamma is equal to 1 divided by radical 1 minus c squared over v squared, and since we've got our v in terms of speed of light, that makes it a little easier. I'll let you work that out, and we get a gamma factor of 7. I'm not sure if it's exactly 7. This is what I have in my notes. So there's going to be that. So now we can say we want a time measured by, okay, that's t naught, or delta t naught. So we can say delta t naught, the time elapsed for this event, is equal to delta t prime divided by gamma. So that's the 1.3 times 10 to the 8th seconds divided by 7. And we get 1.86 times 10 to the 7th seconds, which is basically, I'm sorry, I put light years up here. This is 4.2 years. I think it's easier to look at this in years, 0.67 years. Okay, so there's a significant difference in how much the time we measure. The different frames measure in terms of the actual trip. Okay, so if you're on Earth, you say, well, they just traveled that far, they traveled that speed, so it's a simple distance divided by time, and it took 4.2 years. But on the spaceship, we know that relative to the Earth, time it ticks more slowly. So they, on the spaceship, they only measure 0.67 years, which is significant. That's how much they would say they aged as well during that time. Now, what is the distance between or to Alpha Centauri as measured by the astronauts? Okay, so since the object in question is moving relative to them, they are looking for the length, not the proper length. And so we can use the gamma. We can say L equals L naught divided by gamma. And then this simply becomes the 4 times 10 to the 16th meters divided by 7, which of course is 5.7 times 10 to the 15th meters. Okay, so in other words, it's significantly smaller, 7 times smaller. All right, so let's sum up a few more comments here. Two important results occur when an object moves relativistically. Okay, and that means their velocity is on order of magnitude of the speed of light. Now this is from the stationary frame. If you are on a stationary frame watching somebody else go by and you can see their clocks ticking and you can measure their lengths, you see that time moves more slowly, okay, on the moving frame. And the moving object's length contracts. And it's important that it's in the direction of motion. In other words, any perpendicular motion, you don't see a length contraction, okay? And then if you try to put it all together, let me see if I can scroll down here. Okay, one last comment on okay, we're looking for some consistency between the two frames, and that consistency, that constant, if you will, is the speed of light. So let's show how we can work that out with our equations. Okay, oh, I'm sorry, I jumped ahead. In this point here, okay, it's really important to understand that if I'm on the Earth watching somebody go by at a relativistic speed, I will see a length contraction and a time dilation. But from their frame of reference, they don't see themselves moving. They see us moving, and they would say the same thing as well. Okay, so we want to resolve that in a way with our equations to make sure that there is a consistency there. So if we look closely at the time dilation equation that we had before and the corresponding length contraction L, we can see that what holds them together is this Lorentz factor gamma, and they kind of offset each other in a way that I'll show you. So we have from one equation that the Lorentz factor is simply the proper length divided by the length contraction. In another situation, it's equal to the time dilation divided by the proper time. Okay, so you can go back and look at those equations and see how that works out. Now, if I cross multiply and then solve and make this a speed, a distance divided by time, it works out that I have L naught over delta t prime here, and that's got to equal L over delta t naught. And if you look closely at those and back to the other equations, each one of those is nothing more than the speed of light, which everyone must agree upon. So we see that there is this internal consistency right here that can be lost in trying to figure out all the different measurements that change because of the different frames of references. Okay, in the next one, we're going to talk about some invariant quantities, things that must be measured the same in all frames of references, and how we can put together in slightly more complex equations.